Today we're looking at problem 24 from this year's AMC 12B competition, where we're asked to find the number of solutions that satisfy sine of 20 pi x is equal to log base 20 of x. And so looking at this equation, there's no really obvious way to sort of manipulate it because one side is sine and one side is log. Um, So the other way to solve this problem is to actually draw out both graphs. And what does it mean for a number to be a solution? That's just an intersection point of the two graphs, right? So after we draw them out, we want to see if we can sort of count the number of intersection points between the two graphs. Well, so let's try to do that. Let's draw sine of x, or sine in red. So we have that sine will look something like this. Right. Alright, this will be 0. Gonna have a minimum here of -1, a maximum here of 1. And because it's multiplied by 20 pi in the center, that means its period will be every 1 over 10 increment of x. What that means is this will be, or one period here will be 1 over 10. So every half a period would be 1 over 20. So this would be 1 over 20. Just to keep the denominators the same, this would be 2 over 20. This would be 3 over 20. This would be 4 over 20, and so on. And so what does log base 20 of x look like? This will draw that in blue. Right, log usually looks something like this. Right. And so you can see from like just sort of this tiny approximation, the graphs will only intersect between the range -1 and 1. Right, so we really only care about when log base 20 of x is in this range. And so the idea is we want to find where is it equal to -1 and where is it equal to 1, and then sort of go from there. And so I guess we can try to do that. So we want, for when it sort of enters the graph, we want log base 20 of x to be equal to -1. So this implies x is equal to 1 over 20. And then when it leaves this region, we'll want log base 20 of x is equal to 1. So x is equal to 20. And so sort of marking that, we have the point here, which will be 1 over 20 -1. And then I guess the graph will sort of extend here. Let's say just all the way to out here. One will be at the end of the period. So this will be 1, or 400 over 20. And then the graph will leave at 21. This will be 21 or 20 comma 1. Right, so our graph will sort of look like, or the part that we care about will look something like this, right? And again, I'll extend out here this way, extend below, something like that, but we don't care about those because they'll never intersect sine there. And I guess the one other point we should care about is this x-intercept spot where of the log graph, because then we can sort of split what we're looking at into two cases. One is the part below the x-axis, and then one is the part above the x-axis. And that'll sort of make counting the number of intersection points easier. And so what is this point then? Well, that's just when log base 20 of x is equal to 0. So x is just equal to 1. So we have that this point is 1, 0, and then the graph around, or the sine graph around this area will look something like this, I think. I'll draw one more. Good. Right, it looks something like that. Okay, so now let's start counting, or try to count the number of intersection points. We'll call this first part 1 and the second part 2. And so for 1, I want to write this right here. We can see that, right, looking at each period, right, this, I'm marking it in green, this will be one period, and then this will be one period, and so on. So in this first period, we can see that there are two intersection points, right, here and here. So between 0 to 2 over 20, there are two intersection points. And then similarly from 2 over 20 to 4 over 20, the next period, right here, there are again two intersection points. That gives 2, and right, we can see this pattern continues for each period. Right, for instance, the next period from 4 over 20 to 6 over 20, there are 2, and this will continue for each period until we get to this last period, right? I guess this will be 20 over 20, at least in this region that we're looking at. This will be 18 over 20, right? So all the way until 18 over 20. There will be 2. And so there are a total of 10 periods here, each one with 2. So that's 20 intersection points. And then now we can look at our second region, right, and sort of try to do the same. And just because I guess it's drawn, actually no, we can do it from here. Right, from in the second region, our first period will look at this, or we'll look at this part of the graph, and we see that there are two intersection points, right? One exactly at one, and one there. So let's call this, let's make these intersection points yellow. Right, there, in this first period. So from 20 over, this will be, this point, or this first period here will end at 22 over 20. So from 20 over 20 to 22 over 20, we'll have two intersection points. And then this next period, we'll have, again, two intersection points. So from 22 over 20 to 24 over 20, we'll have two. And again, this pattern will continue all the way to our last period right here, where we'll again have two intersection points. And I guess this last period should start at 398 over 20. So this will continue all the way into 398 over 20 to 400 over 20. We'll have two. And so how many periods do we have in this region? And so the idea is to sort of actually look at just one side and then sort of manipulate it into a sort of, or map it to 1, 2, 3, 4, 5. Right, so we have 22 is one period, 24 is our second period, 26 will be our third period, and so on. So how can we get from 22 to 1? Right, we can divide by 2 and then, or subtract by 20 and then divide by 2. Right, and the idea behind dividing by 2 is because we're incrementing by 2 each time, but we only want to increment by 1. So minus 20 and divide by 2 will yield 1, right, or will be equal to 1. 24 minus 20 divided by 2 will equal to 2. 26 minus 20 divided by 3, or divided by 2, will equal 3. So that's exactly the mapping we want to get the number of periods. So 400 is our last sort of endpoint. So 400 minus 20 divided by 2, that will be 380 divided by 2, or 190. So there are 190 periods, each one again with two intersection points. So that's 380 total intersection points. So it seems like there are 20 plus 380, which is equal to 400 intersection points. But we have to be careful because in this first part, or when we counted the number of intersection points in this first region, notice in this final period that we looked at, the two intersection points are here and at 1, right? But in the second region, the first period also has the intersection point. We also counted the intersection point at 1 again when x is equal to 1 in this other point. So we actually double counted the intersection point at x is equal to 1. So that means we have to subtract 1 from our final answer. to get 399 intersection points or solutions. And that's it.